Hello and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host Lucy Hodgins, and in this bonus episode I got to talk to a bunch of super interesting early careers researchers at the Meet the Faculty Candidates poster session at the Conference of Decision and Control. So this is the chance for graduate and postdoctoral researchers that are looking for an academic position to showcase their work and interact with potential future employers. But it also allowed me to meet lots of wonderful people and ask them lots of questions. This episode is going to give an overview of the research that they are doing, and I have put links to the papers in the description if you would like to get in contact with them. So, get ready to hear all about research in a wide variety of different areas, including strategic communications, traffic control, surgical robotics, reinforcement learning, estimation in networks, and a whole lot more with my guest today from the Meet the Faculty Candidates poster session. So the way that Amy does this in her work is to use a tree data structure, which is a set of connected nodes where each node has a single parent and potentially many children or leaf nodes. Now, each tree data structure corresponds to a particular pair of data points corresponding to the state at the current and next time step. And each level of the tree corresponds to a particular iteration of the algorithm. As Amy described, you start off with an over-approximation of the invariant set, and then at each step of the algorithm, you look at whether the norm ball of a given radius around the state at the next time step is inside or outside of your estimate of the invariant set. If it's completely inside, then the node remains unchanged. If it's completely outside, the point is removed from the invariant set. If this ball intersects partly with the invariant set, then the parent node gets divided into 2 to the power of n leaf nodes, where n is the dimension of the state space, and on the next iteration you consider balls with half the radius. Intuitively, this makes a lot of sense, so you're dividing up the state space and getting rid of bits that aren't in the invariant set, but this paper formalises this mathematically and links it to the synthesis of Lyapunov functions. So in particular, her work provides a way to certify the stability of these kind of systems. And she does this by taking this invariant set and assigning a Lyapunov function value to each partition of this set. And this then gives a discontinuous piecewise constant Lyapunov function that can be used to prove stability. So this is an example of something known as strategic communication, in which communication between two entities can be viewed as a non-cooperative game. So Anju examined this in the presence of noise and where the data to be transmitted is quantized, and was able to characterize the strategies of the two communicating entities at the Nash equilibrium. And it turns out there are quite a few interesting applications or examples of strategic communication. I also wanted to mention that Anju's most recent paper modifies this setup slightly to consider privacy objectives, where the encoder is transmitting a message to balance fidelity with privacy in the presence of an eavesdropper, whilst the decoder just wants to minimize its own estimation error and doesn't care about privacy. So the crux of Brian's research involves defining controllers directly on a partial differential equation, or PDE. So in previous work, he'd used linear quadratic controllers to approach this problem by linearizing the system model, but the work he was presenting at CDC was able to deal with the PDE model more directly. So one standard approach to tackling this has been to discretize the model into a system of ODEs, or ordinary differential equations, and then apply control barrier functions and or control Lyapunov functions to ensure that the system stays within the safety constraints. In contrast, Brian's work presents a unified framework that combines control Lyapunov and control barrier functions in a way that enforces constraint satisfaction directly at the PDE level, which, as he explained, is a lot less computationally intensive. So pi stands for partial integral equation, and this gives a way of expressing PDEs in terms of the evolution of a higher spatial derivative of the state. The PyTools software that Declan mentioned is a free MATLAB toolbox that his group has developed that you can use to manipulate these kind of equations, solve pi inequalities, and design various different controllers. Declan's research focuses mostly on the theoretical side, so looking at how to apply these tools to analysing stability of various problem formulations, including multivariate PDEs, coupled PDEs, and those with delays or periodic boundary conditions. Also, traditionally, this pi formulation only holds for linear PDEs, but Declan's work has extended this idea to scalar quadratic PDEs, which can be used to model kind of fluid dynamics, population growth, that kind of thing. And in this case, you end up with a partial integral operator instead.
Hi, I'm Hamza.
So Hamza has published quite a few interesting theoretical papers, but there are two in particular that I wanted to highlight. So the first one examines the problem of real-time identification in the presence of degraded control authority. So this can be applied to nonlinear affine systems subject to phenomena such as actuator wear and tear, friction, input saturation, dead zone, that kind of thing. And the paper proposes an algorithm to identify these and counteract them as much as possible. Another paper examined the problem of identifying simultaneous sensor and actuator faults in cases where there isn't necessarily sensor redundancy. So the general idea is to fit a sensor degradation map between the expected and sensed output, and then use this to test for sensor degradation. After this, actuator degradation is tested for based on the difference between the guaranteed reachable output set and the confidently reached output set. Then finally, the full state is reconstructed using a zonotopic Gaussian-Kalman filter, which is just a particular kind of estimator that makes use of the fact that the disturbances are bounded within a particular set. This work relates to a paper titled Heat Conduction in Live Tissue During Radiofrequency Electrosurgery and examined how to model this phenomenon and estimate the various parameters. The basic idea here is to apply controlled probing forces to a region of the body and measure the resulting deformation. Hamza then uses these measurements to estimate something called electrostatic signed distance function, which gives a way of representing the 3D curved geometry of the object. In particular, Kirill is looking at applying a technique known as control-based continuation, in which a stabilizing feedback controller steers the system through a sequence of steady states, which may potentially be unstable when trying to observe it open loop. Kirill made use of a proportional controller and also showed that this technique could be used to determine the equilibrium of individual genetic modules and then predict the equilibrium of the system when two of these modules are competing for resources. So, as you just heard, Nick Marios has worked on a ton of very cool areas, combining control with various aspects of machine learning. But I wanted to add a little bit more detail about his work on safe reinforcement learning. So, he released a paper earlier this year that looks at constructing feedback controllers to guarantee closed-loop predefined time stability. And this approach made use of a Lyapunov function that served as the solution to a Hamilton-Jacobi-Bellman equation. And the paper developed a critic-only reinforcement learning-based approach to learn this function in predefined time. I was reading up on some of Parth's papers in this area, and this does seem like super interesting work. So in the first paper I was reading, the aim was to present a distributed estimation algorithm that could estimate a relevant subset of the total variables at each node. And because each node didn't have to estimate all of the variables, this reduced storage, communication, and computational requirements compared to more traditional consensus-based results. Another paper I looked at related to what Parth has just described, so it examined cooperative tracking of time-varying signals whilst preserving privacy, which in this context meant keeping the received signal private from eavesdroppers. It did this by extending the standard state decomposition approach and introducing a mixing step in the initialization to increase privacy whilst maintaining convergence of the estimation. In addition to estimation and control of epidemiological systems, Radoslav has also worked on designing observers for hovercraft, as well as a number of variations of active disturbance rejection control. So, active disturbance rejection control is a technique that can be applied to unknown systems by lumping the dynamics together into some disturbance term and then estimating this using an extended state observer. However, this still requires you to know both the order of the plant and its input gain parameter. So one of Radoslav's papers was carrying out online identification of this input gain in order to remove this requirement. Another of his papers was looking at how to combine this framework with a parameter identifying extended state observer, and showed that by doing this you could ensure asymptotic convergence of both tracking and estimation errors, as well as better transient performance. The final researcher I wanted to mention is Carmen Amo Alonso, who I actually saw give a talk at CDC in the Control Architecture workshop. Her research is so interesting, she was so enthusiastic in the talk that she gave. I really wanted to highlight her research here, even though I didn't manage to get an audio clip from her. So, Carmen does a ton of interesting research on the intersection between control and AI, so viewing AI systems as a dynamical system. And she's looked at this on various different levels of granularity within deep learning architecture. So on the lowest level, she's compared various types of mixer block within the same framework. So these are essentially the building blocks of AI, so things like attention blocks, state space models, and recurrent neural networks. And she also wrote a really nice introduction to the use of state space models in deep learning architectures aimed specifically at control engineers, which I really enjoyed reading. And then right at the other end of the scale, she's worked on how to embed generative AI models into physical systems. So, for example, how best to interface these with more traditional controllers in the context of robotics. So, quick summary of the work of all of these researchers. Amy Strong develops data-driven methods to compute invariant sets for constrained nonlinear systems. Anju Anand studies strategic communication using game theory, modelling how to transmit information under misaligned objectives. Brian Block designs computationally efficient controllers for traffic systems, models as partial differential equations. Declan Jag develops theoretical and computational tools that can be used to solve a wide variety of PDE-based problems. Hamza Al-Kabir advances fault-tolerant control with applications to robotic surgery. Kirill Seshkar uses control-based continuation to probe biological systems by steering them towards interesting equilibrium points. Nick Marios-Kokolakis develops non-asymptotic Lyapunov-based and physics-informed algorithms for robust autonomous systems. Parth Paratosh creates privacy-aware distributed estimation algorithms for time-varying networks. Radoslav Postelski uses finite time estimation to study the spread of epidemics. And finally, Carmen Amo Alonso bridges control theory and AI by modelling deep learning architectures as dynamical systems. That's all from this mini bonus episode. I really hope you've enjoyed it. I, for one, really love meeting all of these researchers and hearing about their work and then reading up on their recent papers. So I do hope you found it interesting. I have left their details in the description if you fancy checking out their work. If you'd like to get in touch, you can connect with me directly or follow the podcast on LinkedIn. As I mentioned at the end of last episode, next month I'll be talking to a wonderful researcher that I interviewed at CDC about her work on game theory, and that'll be released on the 1st of February. But until then, have a fantastic next few weeks.